Welcome to the tutorial sheet 3, in which we are going to see the free response of RLC series and parallel circuits. In today's session we will be discussing only about RLC series circuits. To start with, we are having a series RLC circuit where R is 10 kilo ohms, L is 0.1 millihenries, capacitance is 10 microfarads. We need to identify the damping exhibited by the circuit. We need to identify the damping. Damping means how many types of damping we are having. We are having three types of damping. One is over damped condition, critically damped condition, and the last one is the under damped condition. To start with, to identify the damping condition, we need to find the relationship between alpha and omega naught. If alpha is greater than 0, alpha is greater than omega naught, then the system is over damped. If alpha is equal to omega naught, then the circuit is critically damped. If alpha is less than omega naught, then the RLC circuit is under damped. The given R value, inductance value and capacitance value are specified here. First, let us evaluate the alpha value. Alpha value for a RLC series circuit is R by 2L and omega naught is equal to 1 by square root of LC. Substitute the known values R and L. You will get R value 10 kilo ohms and 2 into L value 0.1 millihenries. If you evaluate, you will get 50 into 10 to the power of 6 as alpha value. Coming to the omega naught, 1 by square root of LC, substitute the value of L 0.1 millihenries into C value 10 microfarads. You will get it as 3 into 162 into 10 to the power of 4. If you observe, the alpha value is greater than omega naught. Both power of 10 and the individual number is greater when compared to the omega naught value. It means the system is over damped. This is the question asked. The response is over damped and the roots are real and negative. How we are saying the roots are real and negative? What are the roots? How are the roots? Roots can be evaluated. It is not asked in the question. If you check the question, this is not there in the question. We no need to identify the value of S1 and S2. This itself, alpha is greater than omega naught. Alpha is greater than omega naught. This only defines that the system is RLC series circuit is over damped. Additionally, just for your information, we have evaluated it here where the roots are S1 and S2. S1 is minus alpha plus square root of alpha square minus omega naught, and S2 is minus alpha minus square root of alpha square minus omega naught. When you evaluate this, you will get the values of S1 and S2. This is not asked in the question. For your information, it has been written here. Coming to the second question, if R is equal to 20 ohms, inductance is equal to 0.6 ohms, what should be the value of C? What should be the value of capacitance in a RLC series circuit for a condition that the circuit is over damped, critically damped and under damped? To identify the over damped and under damped condition, to identify the value of C for over damped and under damped condition, first we need to identify the value of C for critically damped. Why? Because we know the condition for critically damped is alpha is equal to omega naught. How we got alpha is equal to omega naught? If we check these roots, if this value is 0, alpha square minus omega naught square is equal to 0, it means alpha square is equal to omega naught square, then the system is critically damped. Substitute the value of alpha for a RLC series circuit. It is R by 2L the whole square, which is equal to 1 by square root of LC. And as we are having square, it will become 1 by LC. From here, C is equal to 4L by R square. 4L by R square. We need to identify the C values. So C capacitance can be identified as, substitute the value of L 0.6 divided by R 20 square, you will get it as 6 microfarad. 6 into 10 to the power of 6 millifarad, sorry, it is 6 millifarads. It means this is the capacitance value for the RLC series circuit to make the response as a critically damped. If we want the system, the RLC series circuit, to be overdamped, then C should be greater than 6 millifarads. If we want the C should be to be underdamped, then say the RLC circuit should be underdamped, the C should be less than 6 millifarad. These three conditions will form, from these three conditions we can get that overdamped condition, critically damped condition, and underdamped condition for different values of C. Coming to the third question, we need to calculate the value of R. We need to calculate the value of this R which is present in the circuit here, to which a 60 ohm resistance is connected in parallel, and this whole combination is connected in series with the C and L elements. We need to identify the value of R for which the system is critically damped, where the response is critically damped response. Critically damped response means, let us, to identify the critically damped condition, what we need to do is, the condition we know is alpha is equal to omega naught square. Alpha square is equal to omega naught square, or you can write it as omega naught square. I missed square here, you need to write square. Alpha square is equal to omega naught square, or you can write all alpha omega naught is equal to alpha, or omega naught is equal to alpha. What is the value of omega naught or alpha for a critically damped condition? Alpha value for a RLC series circuit, alpha value is equal to R naught by 2L. For a RLC series circuit, alpha value is R naught by 2L. Is it right? But we don't know the R value. To identify the R value, we will represent that this is an equivalent R naught value. We will represent the complete circuit with an equivalent value of R naught. And then for a given RC value, for a given RLC series circuit, alpha is equal to R naught by 2L. And omega naught, if we evaluate omega naught, if you evaluate omega naught is equal to 1 by square root of LC. Substitute the value of L and also C, you will get 5. When omega naught is equal to alpha, we can write it as R by 2L is equal to 5. 5 from here, and the alpha value is given by R naught by 2L for this specific RLC series circuit. From here you can write it as R naught is equal to 10L. We need to identify the L value. How to identify the L value? L value is already given here, no need to identify, which is equal to 4 henries. Then R naught is equal to 40, but we need to evaluate R. What is the relationship between R and R naught? It is given as R into 60 divided by R plus 60. The reason is the equivalent resistance R naught is for the value of for the parallel combination equivalent resistance of R and 60 ohms. Parallel combination of R and 60 ohms. So we can write it as R naught is equal to R into 60 divided by R plus 60. You will get R naught. So as we have evaluated R naught is equal to 40, you can write it as 60 R by R plus 60. This equation is equal to 40. From here 60 R is equal to 40 into R plus 40 into 60. You will get it as R is equal to 120 ohms for critically damped condition. So what we did, initially we have represented these two resistances with a single resistance called R naught. Now it forms an RLC series circuit. Okay, then omega naught is equal to 1 by root LC. We have evaluated the omega naught value, which is 5. For critically damped condition, alpha square is equal to omega naught square, or you can write it as omega naught is equal to alpha, but we know alpha for a RLC series circuit is R by 2L. Here R value is R naught. R naught divided by 2L is equal to 5 ohm, 5, which we have evaluated from here. Now from this expression we can write it as R naught is equal to 10 L, and L is known value 0.01 Farad, sorry, it is 4 henries. Substitute the value of L, you will get it as R naught is equal to 40, and we also know R naught is equal to R into 60 divided by R plus 60. Substitute the value, you will get R is equal to 120. With this we have finished problem number 3. Coming to the problem number 4, we need to find the V of t, voltage across the capacitance. We need to find the voltage across the capacitance in the circuit when the switch moves from position A to position B. Initially the circuit is in position, the switch is connected to position A. So we can write it as, when the switch is in position A, V0 minus is equal to 0, V of 0 minus is equal to 0, IL 0, so the current through the inductor, it means voltage across the capacitance. What is this? V of 0 minus, this is the voltage across the capacitance. Voltage across the capacitance before switching operation, it is not connected to the power supply, hence the voltage across this capacitance will be 0. And what about the current flowing through the inductor? Current flowing through the inductor is the current flowing through the resistance of 30 ohms, and this will be short circuited, and through the 10 ohms. So the current flowing through the series combination of 30 and 10 ohms will be the current flowing through the inductor. So IL before switching operation will be supply voltage divided by 30 plus 10, you will get it as 0.5 amperes. We got the current through the inductor before switching operation, and also voltage across the capacitor before switching operation when the switch is in position A. When the switch is in position B, when it turns to the position of B, if you observe, we are having 3 different elements: inductance, resistance and capacitance. It is a RLC series combination. For a RLC series combination, we need to identify the damping of the response of the system, whether the system is in damped condition, over damped or under damped or critically damped, for which we need to identify the alpha values and omega naught values. Alpha value for a RLC series circuit is R by 2L. Substitute the value of R is 10 ohms, L value is 4, you will get it as 10 by 2 into 4 is equal to 1.25 units. Alpha is equal to 1.25. Now coming to the omega naught angular frequency, which is equal to 1 by square root of LC. Substitute the value of L and C from the circuit. L is 4 and C is 0.24, you will get omega naught is equal to 1. From comparing alpha and omega naught, we can say that alpha is greater than omega naught. When alpha is greater than omega naught, then the response is over damped. Then the circuit is, we can say that the circuit is over damped circuit. For such circuit, let us evaluate the roots of this system. S12 can be written as minus alpha plus or minus square root of alpha square minus omega naught square. If we want to calculate S1 is equal to minus 1.25 plus square root of 1.25 square minus 1 the whole square. Substitute the value of 1.25 and 1, you will get it as minus 0.5 for S1 and S2 as minus 2. S2 as minus 2. We are having 2 roots and both the roots are negative. We are having 2 roots and both the roots are negative. So V of t is equal to A e power, we can write it as V of t is equal to, for a system with overdamped case, for a RLC series circuit with an overdamped case, the voltage across the capacitance V of t is given as AES2 of t. This is the response of the circuit. One of the responses is the voltage. The voltage is given as AES2 of t plus B e power S1 of t. Either you can write S1 here or S2 here. Both we will be getting the same values. Nothing to worry. Keep S1 first and S2 first, no issues. To start with, once we got this equation for an overdamped system, overdamped response of an RLC circuit, V of t is equal to, substitute the value of S2 and S1. S2 is minus 2 and S1 is minus 0.5 t. Once you got once you got this equation, substitute the initial conditions. Initial conditions are the before switching operation. It means at t is equal to 0, at the instant t is equal to 0, substitute the value of 0 here. We will get V of 0 is equal to A into e power minus 2 into 0, e power minus 2 into 0 will become 1. Similarly here e power minus 0.5 into 0, it will also become 1. So V of 0 is equal to A plus B. We got this equation. V of 0 is equal to A plus B. And also we know V of 0 is equal to 0. What it is? Voltage before switching operation. Voltage across the capacitance before switching operation. How much it is? Voltage across the capacitance, it is 0. 0. So you can write A plus B is equal to 0. We got another equation. Now what we know, as it is a RLC series circuit, current flowing through the inductor and the current flowing through the capacitor is same as they are connected in series. As they are connected in series, current flowing through the inductor and current flowing through the capacitor should be same. So current flowing through the capacitor I of L should be equal to, current flowing through the inductor I of L should be equal to current flowing through the capacitor IC should be equal to, and the formula is given as C dV naught by dt. This is the current formula for the capacitance, which is also equal to IL. What is IL? IL before switching operation is 0.5. So we are equating that value here. IC is equal to IL. So IL value what we got is 0.5 under before switching operation. So and the formula for the current flowing through the capacitance is C dV. Voltage across the capacitance is current through the capacitance is C dV naught by dt. From this expression, dV naught by dt is equal to 0.5 by C. We know the value of C. Substitute the value of C 0.25, which is equal to 2. Just we got the value of dV naught by dt is equal to 2. Now next, here we are evaluating dVt of t by dt. What for we are evaluating it? We got the expression here V of t. If you differentiate this dV of t, what for we are doing? I will let you know. Differentiate this equation. dV initially we got an expression in terms of A and B. Again consider the same expression and differentiate it. dV of t by dt, if you differentiate this equation, you will get it as minus 2 dV of t by dt is equal to minus 2 A e power minus 2t minus 2 A e power minus 2t plus minus 0.5 into B e power minus 0.5 t. This expression you will get. Now in this, after differentiation, substitute the value of naught. This is the procedure. Generally we differentiate, we will get one expression and then we will differentiate it with the time. Once we differentiate this, we will get we need to substitute the initial conditions at t is equal to 0. So dV naught by dt is equal to minus 2a minus, substitute the value of 0 here, t is equal to 0. If we substitute, this complete equation will be changed to dV naught by dt is equal to minus 2a minus 0.5 b. Why? Because e power minus 2 into 0 will become 1. E power minus 0.5 into 0 will become 1. So the expression will changes to dV naught by dt is equal to minus 2a minus 0.5 b. But we know dV naught by dt, which has been evaluated here. dV naught by dt is, we got it as 2. Okay, we got, so simply we got one equation a plus b is equal to 0 and another equation minus 2a minus 0.5b is equal to 2. When we simplify, when we solve these two equations, here I can write it as a plus b is equal to 0, or you can write it as 2a plus 2b is equal to 0, and this expression, if you simplify them, you will get 1.5b is equal to 2, or b is to 1.33. And we also know, as a plus b is equal to 0, then a is equal to minus b, b will be, or a is equal to minus 1.1 minus 1.333. The complete expression of v of t can be written as v of t is equal to minus 1.33 e power minus 2t plus, this is, this expression what we got, this expression is a e power minus 2t. So in place of minus 2t, in play to the coefficient of e power minus 2t, we need to write a is minus 1.33. Coming to the coefficient of e power minus 0.5, it is coefficient of minus 0.55 is b, so we will be writing it as b, we will be writing it as 1.33 e power minus 0.5 t. This completes your voltage across the equation for the voltage across the capacitance. Now coming to the next part, here if we observe problem number 3, the responses of a RLC series circuit as Vc of t is equal to 30 minus 10 e power minus 20 t plus 30 e power minus 10 t. IL, current through the inductor, is equal to 40 e power minus 20 t minus 60 e power minus 10 t milliamperes. What does it mean? Initially the circuit has been given and we need to identify the responses, whereas here the responses are given, we need to identify the parameters RLC. This is a reverse, we are flowing, we will be following the reverse procedure. So simply we know Vc of t is equal to 30 e power minus 10 e power minus 20 t plus 30, means what, voltage, there is some initial voltage of 30 is was existed in the circuit, and then whatever it is, whether it is initial voltage is there or not, nothing to be worried. What we need to identify is the value of R, L and C. 3 different values has to be identified. To start with, the given expression, we have, there are 2 responses from the circuit. One response is voltage across the capacitance, another response is the current through the inductor. Voltage across the capacitance and the current through the inductor, if you observe, we are having e power minus 10 t, e power minus 10 t, and also e power minus 20 t minus 20 t. It means what, these responses we can write it as S1 is equal to minus 10 and S2 is equal to minus 20. The reason is the positive term, out of these two, the positive term, how is positive term prepared? If you check the positive term, the positive term is prepared by minus alpha plus S1 is the positive term, so S1 is equal to minus alpha plus square root of alpha square minus omega naught square. What is S2? S2 is minus alpha minus square root of alpha square minus omega naught square. It means the negative parameter, minus alpha minus square root of alpha square minus omega naught, will have more negative value when compared to the minus alpha plus square root of alpha square minus omega naught. Considering this, we can write it as S1 is equal to minus 10. Why? Because the positive value should be less and the negative value should be, the second root should have more negative value. So we can write it as the first root will be S1 is equal to minus 10 and S2, the second root will be S2 is equal to minus 20 ohms. Now we know S1 two roots are given by minus alpha plus or minus square root of alpha square minus beta square. It means for S1 is equal to minus alpha plus square root of alpha square minus omega naught. S2 is equal to minus alpha minus square root of alpha square minus omega naught. if you add these two roots s1 and s2, if you add s1 and s2, the negative and positive terms both will be get cancelled. The remaining parameter will be minus 2 alpha, minus alpha plus square root of alpha square minus omega naught plus of minus alpha minus square root of alpha square minus omega naught. The negative, the square term, the square root parameter will be get eliminated, only minus 2 alpha will be existing. Minus 2 alpha will be existing, and which is equal to minus 30, which is equal to minus 30. How we got s1 and s2? We need to add minus 30 plus of minus 20. Minus 10 plus of minus 20 will be equal to minus 30. So minus 2 alpha, from this expression we got minus 2 alpha, from these two parameters we got minus 30. So we can write it as alpha is equal to 15. So we can write alpha is equal to 15 from this relationship. And we also know for RLC series circuit, alpha is equal to R by 2L. So in place of alpha, substitute R by 2L, you will get R is equal to 15 into 2L, which is equal to 30L. From here, we got a relation called R is equal to 30L. We know S1 is equal to minus 15 plus square root of 15 square minus omega naught square, which is equal to minus 10. We also know alpha square minus omega naught square is equal to 25. How we got this 25? Alpha square minus omega naught square from this expression. From this expression, we can write it as square root of 15 square minus omega square is equal to it will become plus. I think there is some calculation mistake here. Is it right? Yes, there is some calculation mistake. It will become plus here. The procedure will be same. It is not 25. It will be a different value. You need to calculate. You need to solve and submit it. For this value, I am doing it now. From here, you can get omega naught is equal to square root of 200, which is equal to 14.14, or omega naught is equal to 1 by square root of L, which is equal to square root of 200. For time being, we will say that this is the value. When this is the value, LC is equal to 1 by 200. No, it's the right value. How? Because the difference between minus 15 and minus 10 will be 5, and if you want to remove this squaring on both sides, square root, if you want to remove this square root, you need to square on both sides, so then you will be getting 15 square minus omega naught square is equal to 25. This is 225, 15 square is 225. When you differentiate, when you remove this, when you subtract 25 from 225, you will get it as 200. Omega naught square is equal to 200, so omega naught is equal to square root of 200, which is equal to 14.14. We also know omega naught is equal to 1 by square root of LC, or LC is equal to 1 by 200, or LC is equal to 1 by 200. This is one other relationship. Since RLC series circuit, IC is equal to IL. Current flowing through the capacitor should be equal to current flowing through the inductor, which is also equal to current. Another expression to evaluate the current flowing through the capacitor in terms of voltage can be written as C dV by dt. Voltage across the capacitor differentiated by respect to time. So from here you can write it as IL by C. Bring C this side, you will get IL by C is equal to dVC by dt. We know voltage across the capacitor is given in the problem. Substitute the value 30. See here, voltage across the capacitor is 30 minus 10 e power minus 20 t plus 30 e power minus 10 t. 30 minus 10 e power 10 e power minus 20 t plus 30 e power minus 10 t. Now differentiation of a constant will become 0, and it can be written as minus 10 e power minus 20 t into minus 20, so it will become plus 200 e power minus 20 t, and this will become plus 30 into minus 10 e power minus 10 t, so it will be written as minus 300 e power minus 10 t. So now we know the value of C. C is 100 check the question. C value, I think we have evaluated before. C value as 100. C, where is the value of C? We need to identify the C. Yeah, sorry, what we are doing is, C is here, we brought the C parameter this side, and from here we have taken the 100 common. So 100 into C into 2 e power minus 20t minus 3 e power minus 10t. From this parameter we have taken 100 common, and C in the denominator has moved to the numerator and to the other side. This forms your current through the inductor. This one, and we also know current through the inductor as this parameter, current through the inductor. It is given in the question. Current through the inductor 40 e power minus 20t minus 60 e power minus 10t milliamperes. So in place of IL we will be writing this parameter. In place of IL we will be writing the equation given in the problem. When we write it here, it is in milliamperes. It is in milliamperes, so it should be 10 power minus 3, 100C 2 e power minus 20t minus 3 e power minus 10t. From this expression we will be taking 20 into 10 power minus 3 as common. When we take 20 into 10 power minus 3, 20 into 2 will become 40 e power minus 20t, and then from here 3 e power minus 10t, and this expression will get cancelled. We will get it as 20 into 10 power minus 3 is equal to 100C, and C is equal to 20 into 10 to the power of minus 3 divided by 10 square. On the whole, you can write it as 200 into 10 to the power of minus 6, or C is equal to 200 microfarad. And we also know L is equal to 1 by C into 200. 1 by C into 200. Substitute the value of C. 200 into 10 to the power of minus 6, you will get it as 25 Henry. L is equal to 25 Henry, and R is equal to 30 L. We replace the value of L with 25, you will get it as 750 ohms. So R is 750 ohms, L is 25 ohms, and C is equal to 200 microfarads. With this we have finished question number 5. Coming to the question number 6, we need to find the current flowing through the system I of t. This current, if you go to the problem, current I of t is the current through the capacitance. Current through the capacitor, which is also the current through the inductor. Find I of t for t greater than 0 in the circuit. At t is equal to 0, I naught of 0, it means before switching operation. Before switching operation, this capacitance will be open circuited and this will be short circuited. When this part, this inductor is short circuited but this is open, we can say that current in this branch will be 0. When capacitance is open, the current through this branch will be 0. So I of L will be 0 before 0. I of L of 0, or current I of 0 will be 0. And the voltage across the capacitance when under open conditions will be equal to the voltage across the 40 ohms resistance, which is equal to 30 into 40 divided by 10 plus 40. You will get it. This is by voltage division method. This is the loop. 30 volts is getting divided between 10 ohms and 40 ohms. 30 into 40 divided by 10 plus 40, you will get it as total voltage into same resistance where we are going to evaluate divided by the total resistance. 1200 divided by 50, you will get it as 24 volts. Then after t is equal to 0, now after switching operation, the switch is open. When the switch is open, there exists a circuit consisting of R, L and C. All the four elements are in series, out of which 2 elements are resistance. This forms your RLC circuit without any excitation. When there is no excitation, then the system is RLC series circuit with free response. We can say that it is a free response RLC series circuit. When the circuit is in RLC series, 3 elements are existing. We need to identify the damping situation. The damping situation, to identify the damping situation, we need to evaluate alpha and omega naught. Alpha is given by r by 2l and omega naught is equal to 1 by square root of LC. Substitute the value of r in the RLC circuit is 40 and 60. Both are in series, so we can write it as 40 plus 60 divided by 2 into L value is 2.5. You will get it as 20. And if you evaluate omega naught, 1 by root LC, 1 by square root of C value is 1 millifarad, so 10 power minus 3, and this is 2.5, you will get it as 20. So alpha and omega naught both are same. When both are same, alpha is equal to omega naught, then the system is critically damped. For a critically damped condition, the response I of t is equal to, for RLC series circuit, I of t is equal to a plus bt into e power minus st. So I of t is equal to a plus bt into s value. How to evaluate s? How to evaluate s? If you observe, the alpha and omega naught are equal, and this form the root of the system. So we can write it as I of t is equal to a plus bt into e power minus st, where s is the same value what we got it here. Substitute the value here, you will get it as alpha plus bt e power minus 20t, and this value is equal to, at t is equal to 0, when I substitute t is equal to 0, I of 0 will become a plus b of 0 into e power minus 20 into 0. You will get it as I of I naught current before switching operation is equal to a, but we know I of 0 is equal to 0. How we got it from here? I of 0 is equal to 0. I of 0 is equal to a, which is equal to 0. Now we got this equation, minus 20t, we got this equation. Now differentiate this equation, dA of t by dt with respect to time, you will get it as first into differentiation of second, a plus bt e power minus 20t into a plus bt into first into differentiation of second, e power minus 20t into minus 20 plus second e power minus 20t plus differentiation of first means 0 plus bt, 0 plus b of differentiation of t is 1, so a 0 plus b you will get, 0 plus b is, you can write it as b. So the complete expression will be changed to, when you simplify this, you will get it as di by dt is equal to, substitute the value of 0 also, substitute the value of a is equal to 0. If you substitute, you will get it as dA by dt is equal to be power minus 20, be power minus 20, is it right, minus 20 bt, yeah, we got this expression, e power minus 20t here, minus 20 bt e power minus 20t, this expression is here, and a into minus 20 into e power minus 20t is here, and this complete expression will become 0 if you substitute I naught is equal to 0. If you substitute t is equal to 0 in this expression, if you substitute t is equal to 0, a term will become 0, this complete parameter will become 0, as we got a is equal to 0, and if you substitute t is equal to 0, this complete expression will become 0, and you will get only b. So di naught of dt should be equal to b, will be equal to b. This expression is written here. This complete expression, after substituting t is equal to 0, you will get di naught by dt is equal to b. Now we got this expression. Now we need to identify To identify the current flowing through the circuit, the only hint that we have is the current. One option is current through the inductor and current through the capacitor is same, and also sum of the voltages in a closed circuit is equal to 0. Sum of the voltages in a closed circuit, if we check this circuit, voltage across the resistance plus voltage across the capacitance plus voltage across the inductance is equal to 0. So the voltage across the capacitance inductance is given by L di by dt plus voltage across the resistance I of t plus voltage across the capacitance should be equal to 0 by applying Kirchhoff's voltage law. At what instant we are applying? At the instant when the known where the values are known. We know the values of the voltage and current during the switching operations. At the instant when t is equal to 0. At the instant when t is equal to 0, voltage across the inductance plus voltage across the resistance plus voltage across the capacitance is should be equal to 0. Why we are going for this condition? As we know the values of the current and also the voltage and at switching operation. The value of di by d naught t, it has been evaluated here, di naught by dt, di naught by dt here, di naught by dt. This value is equal to b, L into b plus r into I naught value, this value is 0 plus Vc of 0, voltage across the capacitance, Vc of 0 is 24 volts, substitute all these things from here. Di by dt naught is equal to 1 by L into r into I naught plus Vc naught. Okay, L I am shifting it here. L value we know, it is 2.5. Current before switching operation is 0, so 0 into R will become 0 plus voltage across the capacitance is 24 volts before switching operation. You will get B is equal to minus 9.6. So I of t is equal to 0 plus 0 minus 9.6t into e power minus 20t, or simply you can write it as I of t is equal to minus 9.6 into 9.6t into e power minus 20t. With this we have finished RLC free response of an RLC series circuit. In the next session we will be seeing the problems related to the free response of RL circuits. If you are having any doubts, you can